is Max Herrbach, and I'm going to be doing the final assessment, which is the combined loading problem that we were given. So, enjoy. Okay, so we are given a machine component with points A, B, D, and we are focusing on point H right here. So we are tasked with finding the principal stresses and the max shear force at point H. So first thing I will do is find the area real quick, and that's denoted by 40 millimeters and 20 millimeters. I'm going to change this into meters, make this easier. So 0.02 meters times 0.04 meters is 8 times 10 to the negative fourth meters squared. We have the x direction going in this direction right here, the y in the upward direction, z out here. So the first thing I will do is make a cut at H and draw that diagram. I'm going to draw that right here. It's not too bad. So, given from the diagram above, we know that there's a 0.5 kilonewton force in the negative y direction and a 3 kilonewton in the negative x and a 2.5 kilonewton in the negative z. So, point H will be right here. And the dimensions, I'm going to change these to meters. So 0.15 meters and 0.16 meters. Okay, so we are going to have a reaction in the y here, a reaction in the x, reaction in the z. We'll also have moments, so I'm going to draw the moments. Moment in the x, moment in the y. Okay, so to find these moments, I'm going to do the load analysis that we've learned. So load, we're going to have the position I, j, k. Force vector I, j, k. And the moment I, j, k. So the first load I'm going to analyze is the 3 kilonewton load. So the position for this, we know that it is 0.15 in the positive x direction. So that's 0.15 meters, and it doesn't move in the z nor the y. So that's just 0 and 0 for j and k. And the force we know is in the negative x direction, so that's a negative 3 kilonewtons, 0 and 0. All right, for the next one, 0.5 kilonewtons, we have the force in the 0.15 meters in the x direction. And this also doesn't move in the y or the z, so that's just 0 and 0. For the force, we know that it is in the negative y direction. So that's 0 and negative 0.5 kilonewtons, 0. Now we have a 2.5 kilonewton load, and we know that it is 0.15 meters in the positive x and 0.16 in the positive z. So that's how it comes out here. So that's 0.15, 0, 0.16 meters. As for the force, it is in the negative z, so that's 0, 0, negative 2.5 kilonewtons. As for the moment, we know that the moment equals r cross f. So I'm going to do the cross product here and figure out these moment values. So we know that I cross j equals k. and we have an I value here and an I value here. So that's the forces we're going to be multiplying by. So I cross I is equal to 0. So that means there's no moment for this load. And for the 0.5 kilonewton, we have an I and a J, so that's I cross J equals K. So that's 0.15 times negative 0.5. That is a negative 0.075 in the K direction, kilonewton meters. As for the 2.5 load, we know that I cross J equals K, which is right here. And how I learned it is we can move the K out here and move this value in here. So K cross I equals J now. So since we have an I cross K here, we need to reverse this equation. So I cross K equals, now it will be a negative J. And we have 0.15 times negative 2.5. That gives us a negative 0.375. However, we need it to be a negative J. So this would be J, and then multiply that a negative to give us a negative J. So that is 0.375 kilonewton meters and 0. Okay, so for the Rx, we are going to have 3 kilonewtons. So we are going to flip the sign of it. So since this is a negative originally, now it's going to be a positive, because this is what is actually happening in the force and the position, and the moment is the reaction. So we need to flip that sign to account for that. So Ry then equals 0.5 kilonewtons here. Flip the sign since it's a negative here. Rz is equal to 2.5 kilonewtons. And moment in the x, there is no moment in the x as there's no values in this column besides 0. Moment in the y is equal to so this will be a negative since we're flipping that sign again. Negative 0.375 kilonewton meters. Moment in the z is 0.075 kilonewton meters. Okay, so the first thing that we are going to solve for is the reaction in the x. And we know that reaction in the x would be an axial force as we're looking, we're going to look from the z-axis. Look. So looking from the z, this cut is going to look like this. We're going to have h up here. We have a positive x direction here and a positive y. So as we can see here, this is a positive 3 kilonewtons. So this is going to be moving in the 3 kilonewton, in the positive x direction. So we know that sigma x, stress in the x, is P over A. So since this is compressing on this object, this force, it's going to be a compressive force, so that's going to be a negative 3 kilonewtons divided by the area, which we found to be 8 times 10 to the negative 4th meters squared. So solving for that, we get a negative 3,750 kilopascal stress. Okay, so now we can make our stress blocks here for Rx. We know that this is what these stress blocks will look like. We have the XY, XZ, and the ZY. So we have a stress in the X direction here. So we're going to have, sorry, it's actually going to be a compressive force because it is a negative right here. So these arrows are going to pointing inward in the negative X direction. So that is 3,750 kilopascal load for Rx. Okay. And for Ry, it is going to be transverse shear. And we're going to have to look down the Z again. Look from Z. So that's going to be the same cut as above with H up here, positive X, positive Y, and the Ry force is 0.5, positive 0.5 kilonewtons. So that's going to be up here, 0.5 kilonewtons. Okay, so we need to look at this end view of this. So we're going to flip this way like this. So H is going to be up here. The neutral axis is going to be here. So we know that Q equals Y bar prime A prime. And Y is the outward area. So there's going to be no outward area for this point H right here. So that means Q equals 0, which translates to the shear in the XY plane right here, then is equal to 0 right here. Okay, so we are going to go make our stress box for that, which is just going to be nothing. So I don't necessarily need to make these stress blocks, but for the combined loading, it'll be easy to see how that works. Okay, so now we are going to do the reaction in the Z. So we have another transverse shear right here. So we are going to look from the Y this time. From the Y. Okay. So this cut is going to look like this, with H being right here. And we're going to have positive X direction this way and the positive Z direction this way. So we know that right here we have a 2.5 kilonewton load, so that's positive. So that's going to be downward and 2.5 kilonewtons. So the transverse shear equation for a rectangular cross section is 3V over 2A. And we know that this transverse shear is in the X and Z plane. So that's transverse in the X and Z. It's equal to 3 times V, which is the shear stress right here, 2.5 kilonewtons, divided by 2 times the area, 8 times 10 to the negative 4th meters squared. I'm going to solve for that real quick. So we get a 4,687.5 kilopascal shear stress right there. So RZ so we have the XY, XZ, Z, Y. So we know that the shear stress is going to be in the XZ plane. So we need a shear stress that looks like this. Oh, I did that for the wrong stress box. That'll be right here. This would be a positive slope in this case. So that's 4687.5 kilopascals. Now we have a moment in the x. So we found the moment in the x to be 0 as a moment in the x equals 0 because r cross f gave us no values in that x direction for all loads. So I'm just going to draw this again. I don't necessarily need to draw it. Just like the reaction in the y. However, it makes these combined loading diagrams easier to comprehend. So now we are going to move on to the moment in the y direction right here. So moment in the y will be a bending force. So we are going to have to look down the y to observe that momentum, or sorry, that moment. So looking down the y, we are going to have h right here, positive x, positive z. We know that the moment in the y right here is a negative 0.375 kilonewton meter. So that is going to be a clockwise moment of 0.375 kilonewton meters. So we know that there is going to be a stress in the x direction here, where stress equals my over I. So y is going to be the outermost area. Or sorry, y is the distance to the outermost fiber from that point to outer fiber. So in this case, there would be 0.375 kilonewton meter moment here. However, the outward area for this, or the the distance to that point, to the outermost fiber, would be 0 at this point. So we are going to observe that the moment in the y bending is equal to 0. So let's draw this out here with the moment in the y. And there will be nothing on the stress box. As for the moment in the z, we are going to have to look down the z-axis. So this cut is going to look like we have a positive x here, positive y here. So from this value up here, we have a 0.075 kilonewton meter moment there. So that's going to be a counterclockwise moment on this diagram where h is going to be up top here. So sigma x equal to my over I. So the moment is 0.075 kilonewton meters times y in this case would be the radius, or just half the length of the height. So that's 0.01 meters. 0.01 meters. I will be equal to 1/12 the base times the height cubed. That's for a rectangular cross section. So that is equal to 1/12 times 0.04 times 0.02 cubed. So that is equal to 2.667 times 10 to the -8th. So I'm going to plug this in here. That is meters to the 4th. So 2.667 times 10 to the -8th meters to the 4th is equal to 0.075 times 0.01 divided by 2.67. So this gives 28,089.89 kilopascals. So on this moment in the Z stress block, so we have in the x direction a stress of 28,089.89 kilopascals. So this is going to be in tension here. In the x plane, so that's 28,089.89 kilopascals. Okay, so we just did all of the forces in the XYZ and all the moments in the XYZ. So what we can do now is we can create a combined loading here. Make this slightly bigger so it's easier to see. XY, XZ, ZY. Create this box right here. So we have a compressive, so for the X direction, let's say we have a compressive force of 3,750 and another force right here in tension of 28,089.89. So I'm going to subtract this compressive force by the tensile force, or stress, sorry. So that gives a tensile stress in the X direction of 24340 kilopascals. And since this, in the reaction in the Z, we have a shear stress of this value right here, there is no other shear stress value in this plane, the XZ or the XY or the ZY. So that will go uninterrupted and will remain the same value. 4687.5 kilopascals. Okay, perfect. So from these values, we can find the plane of max stress. So the plane of max stress is the XYZ, as there's a shear force and a normal force here. So that is the XZ plane. So with this, we can find our max shear force as well as our principal stresses through this equation that we've seen many times. So theta, or sigma x plus sigma z, as we're in the XZ plane, divided by 2 plus or minus sigma x plus sigma z divided by 2 squared plus tau xz squared. So as we can see in this, there's only stress in the x, so that's 24, 30, 40. Stress in the z is 0. If there was a stress in the z, there would be a tensile or compressive force in this axis right here, and there would be one here as well, but there's not. So that's is equal to 0. Tau xz equal to 4687.5 kilopascals. So now we can just plug these in. We have 24340 plus 0 divided by 2 plus or minus square root of 24340 plus 0 divided by 2 squared plus 4687.5 squared. Okay, I'm going to quickly solve for these values. Okay, so for the first stress, which is going to be the max stress, it is 12,170 plus 13,041.53. So that will equal 12,170 plus that. That is 25,211.5 kilopascals, which is just 25.21 megapascals. For the second stress, I'm going to subtract this value minus this value. So 12,170 minus 13,041.53. That gives us a negative 871.5 kilopascals right here. It's equal to negative 0.8715 megapascals. And the max shear right here is supposed to be max, is equal to this whole value right here. So we solve for that right here, so that's just 13,041.53 is equal to 13.04 megapascals. So from this load, from these loadings right here, we solve for the position, force, and the moment, and we got these values right here. we found that the Rx was an axial load, so we had to look from the Z to solve for this compressive stress right here. We found that Ry, the transverse shear, is equal to 0 because there's no outward area at this point H. And Rz is the transverse shear as well, and we have to look from the Y this time. We found that the cross-sectional area, cross-sectional shear stress to be 3V over 2A. And we plugged in there, found this value. Moment in the X is equal to 0, as we found through our load analysis right here. Moment in the Y, bending 0 because Y is 0 in this problem. And MZ, the moment in the Z, we found I to be 2.667 times 10 to the negative 8th meters to the 4th. Plug that in here, we found Y bar to be the height divided by 2, which is 0.01, times this counterclockwise positive moment in the Z. Found that value, and then from our stress blocks here, we subtracted this compressive load, compressive stress in the X minus this stress in the X for the moment in the Z, and we got 24,340 kilopascals. And we took just the same shear stress in the XZ plane and added that to our combined loading problem right here. From that, we got our principal stress 1, principal stress 2. So this is the max, the minimum, and the max shearing stress as well. Perfect. Thank you.